In this lesson, we're going to discuss the measures of position and also talk about outliers. So to start here, we're going to talk about the z-score. So the z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. There's both a population z-score and a sample z-score, but it's the same process. We just use the proper notations. So to find the z-score, you take the data value x that you're interested in, you subtract the mean, and you divide by the standard deviation. It's the same thing for your sample z-score. So it's important to note that the z-score is unitless, and what it does is it standardizes the data. So once you find the z-score, you're comparing it to a mean of 0, and the standard deviation would be 1. So the purpose of this is to compare things of different populations. So for example, if we are comparing ACT scores and SAT scores, it doesn't make sense to compare the averages of the two or what score you got on it because their numbers are so different. ACT you can score from 1 to 36, and SAT you can score from 400 to 1600. So if we compare someone who got a 33 on the ACT to a person who got an 800 on the SAT, we want to be able to standardize both sets of that data so that they are now comparable. And in order to do that, we find the z-score. So here's an example. The mean upper arm length of 19-year-old males is 38.6 centimeters with a standard deviation of 2.9 centimeters. The mean upper arm length of 19-year-old females is 35.8 centimeters with a standard deviation of 2.8 centimeters. Who has a relatively longer upper arm length? A male whose upper arm length is 41.1 centimeters or a female whose upper arm length is 38.4 centimeters? So the question is, who has a relatively longer upper arm length? So we're going to find the z-score so that we can compare the two. So we need the mean of the male, which is 38.6 centimeters, standard deviation of the male, which is 2.9 centimeters, and the data value we're interested in for the male is 41.1 centimeters. The mean of the female arm length is 35.8 centimeters. The standard deviation is 2.8 centimeters. And the x value of the female we're interested in is 38.4 centimeters. So if we find the z-score for the male, we would take the data value, 41.4 centimeters, minus the mean, which is 38.6 centimeters, and divide by the standard deviation, which is 2.9 centimeters. Doing that, we get 2.5 centimeters over 2.9 centimeters. So here's to show how the z-score becomes unitless because the units centimeters cancel out, and the z-score of the male is 0.862, and that's unitless. So that means compared to the mean of 0, that arm length of 41.1 centimeters is 0.862 standard deviations away from the mean. So it's less than 1 standard deviation away. If we find the z-score of the female, we're going to take 38.4 minus 35.8 divided by the standard deviation of 2.8. That's 2.6 centimeters divided by 2.8 centimeters. Again, that shows how it is unitless. So when you divide those, the z-score of the female is equal to 0.929. So that female arm length is 0.929 standard deviations away from the mean once we have standardized it to compare it to the male. So when comparing the z-scores, the female's z-score is larger than the male's, so that means it's further from the mean than the male's. And since it's positive, it would be above the mean. So in our case here, that means the female has a relatively longer upper arm length than the male. Okay? You can get a negative z-score. What that means is it would be that many standard deviations below the mean. Okay, so positive z-scores would be above the mean. Negative z-scores are below the mean. And you can also use, if you know what the z-score is, you can figure out what does the data point need to be. So there's a possibility you'll be using this formula in solving in your homework assignment. So if you have any questions about that, make sure you let me know. All right, so moving on to objective 2, which is percentiles. So the kth percentile, definition of that, also we noted P sub k, is a set of data such that k% of the observations are less than or equal to that value. So, for example, especially when you're younger, you go to the doctor and you're told, your son's height is in the 70th percentile, or head circumference is a main one, and so is weight. So weight, size, and head circumference. Weight, height, and head circumference are your main ones with your pediatrician. But what that means is if you're in the 70th percentile for height, that means 70% of those your gender and in your age group are the same or shorter than you. Okay? So the percentile represents how many people are less than or equal to that specific value. So for example, like your P sub 98, that's your 98th percentile. So that means 98% of whatever we're talking about is below or equal to you, which also puts you in the top 2%. So like the 99th percentile means you're in the top 1% of the group. So another way we use percentiles is with test scores. Maybe you were in the 90th percentile. That means 90% of your classmates scored the same or below you, and that would put you in the top 10%. All right. So interpreting a percentile here, the GRE is a test required for admission to many U.S. graduate schools. University of Pittsburgh Graduate School of Public Health requires a GRE score of no less than the 70th percentile for admission into their Human Genetics MPH or MS program. Interpret the admissions requirement. So I already have that typed up there. So if you're trying to get into this program, you want your GRE score to be greater than or equal to the 70th percentile. So thinking on the other end of that, to be admitted to the Human MPH or MS program, you need to test into the top 30% on the GRE. All right. All right, so our third objective here, percentiles can fall into quartiles. So they're just specific, quartiles are just specific percentiles. So quartiles divide the data sets into fourths or 4 equal parts. You'll have your first quartile, your second quartile, and your third quartile. So looking at this number line, what that means is your first quartile, that would be the same thing as saying the 25th percentile. That means 25% of the data is at or below that number. Your second quartile is your median. That's just your 50th percentile. So 50% of the data is below that number, 50% of the data is above. Your third quartile is the same thing as your 75th percentile. So 75% of the data is at or below that number, and 25% would be above that. And then remember, you have your smallest data value, which is your min, and your largest, which is your max. Okay, so we'll be using that to create a box plot later on, but quartiles are just special percentiles. So how we find the quartiles is listed there in steps. So we're going to do this with example 3 here. We've worked with this data set a lot. It's talking about the travel time in minutes of that startup web company. To find the quartiles, the first thing we need to do is order the data from smallest to largest. So from smallest to largest, this data set would be 5, 18, 23, 23, 26, 36, 43. All right, we have found the median before. The median is the second quartile. So you work your way to the middle. So our median is 23. So that means the numbers after the median is the top half of the data, and the numbers below the median is the bottom half of the data. So to find your first quartile, look at the bottom half of the data and find the median of that bottom half. So the median of that bottom half would be 18. So our first quartile is 18. And then our third quartile is the median of the top half, which would be 36. All right, so there we have how to find quartiles by hand, which you're really only going to do with a small set of data. The more applicable way to do this would be using StatCrunch in our case, and with larger sets of data, because that's most likely what you're going to have if you're conducting a good study. So to find quartiles using StatCrunch, I'll show you here. We're actually going to use the Chicago salaries data that we've already used. And we're going to determine and interpret the quartiles for the annual salaries. All right, so that's in StatCrunch. Remember, it's under data sets from your textbook, under chapter 3 at the very bottom. I have it pulled up here. So if we just go to stat and summary stats, we're finding it of the annual salary. I'm going to unselect. I'm just going to keep it to what we want. So we want the median, and we can do min max, quartile 1, and quartile 3. Let's just leave it at that. Okay, so there you can see the median of our data set is the 90,024. Our first quartile is 76,266. And our third quartile is 96,060. All right, so we got quartile 1 was the 76,266. The median was 90,024. And quartile 3 was 96,060. So interpreting that, okay, so the first quartile, that means 25% of, we're talking about Chicago public employees, make less than or equal to $76,266 per year. All right. So the median would mean that 50% of Chicago public employees make less than or equal to $90,024 per year. And then your third quartile is representing the 75th percentile. So 75% of Chicago public employees make less than or equal to $96,060 per year. Okay, so your quartiles are just those special percentiles, and it means that that percent in your data set are less than or equal to that number. So in our case, we were talking about the annual salaries of the Chicago public employees. All right, next here we have determining and interpreting the interquartile range. So remember, the range of a data set is the max minus the min. Well, the interquartile range, which we refer to as IQR, it's the range of the middle 50% of the observations in a data set. So the formula to find that is you take the third quartile minus the first quartile. So from the Chicago salaries, the interquartile range would be the third quartile, which is 96,060, minus the first quartile, which was 76,266, which is $19,794. So interpreting that just means the range of the middle 50% of the Chicago public employee salaries is $19,794. Okay, and that's a stat that can be found in StatCrunch as well. So if I just go and edit my options here, you hit Control and also select IQR. And there it is at 19,794. Okay, so here's just a summary of when should we report what measures. So if we, well, the first thing you need to do is look at a picture first. Okay, so first, look at a picture, look at a diagram, a chart, a graph, so that you can see, is it symmetric or is it skewed left or right? So if it's symmetric data, then you want to use the mean to describe the typical value. And then use standard deviation to describe the horizontal spread. Okay, so that's if you're working with symmetric data. If you're working with data that's skewed left or skewed right, you want to use the median and the interquartile range. So if you happen to be comparing data, if you're comparing two symmetrical sets of data, use the mean and the standard deviation. If you are comparing two skewed sets of data, use the median and the interquartile range. If you are comparing a symmetrical set of data to skewed data, you would want to use the median and interquartile range. So only use the mean and the standard deviation to describe the data when you're comparing symmetric data. And last thing here is checking a set of data for outliers. So we talked about how extreme values would affect the mean and the median previously. So those extreme observations are considered outliers. They could be by chance, an error in the measurement of a variable during data entry, or from errors in sampling. So to check for outliers, we have to find our lower fence and our upper fence. So those are cutoff points. So lower fence and upper fence. To find the lower fence, we're going to take the first quartile and subtract 1.5 times the interquartile range. And to find the upper fence, we are going to add 1.5 times the interquartile range to the third quartile. So to check for outliers, let's do this for the Chicago salaries data. All right, so we've already found these. I'm just going to jot them down here. First quartile was 76 to 66. The third quartile was 96,060. And then our interquartile range was 19,794. So our lower fence, we're going to take the first quartile and subtract 1.5 times the interquartile range. And when you do that math, you get 46,575. Our upper fence is going to equal the third quartile, which is 96,060, plus 1.5 times our interquartile range. That is going to equal 125,751. So what that means is any salaries below our lower fence of 46,575 and above our upper fence of 125,751 are considered outliers. All right, so let's look at our data set to see if we have outliers. So what I'm going to do is I'm going to organize this in ascending order, and any number smaller than 46,575. So if I look at this data set, there are tons of salaries below 46,575. So those would all be outliers. And then if I order it the other way from largest to smallest, I'm looking for numbers larger than 125,751. And if you look at these numbers, there are tons of them as well. So there's a lot of outliers here. So that could be pulling the mean either above or below, just depending on how it affects. So to maybe make this a better study or a better data set, maybe we add some variables to it, such as, how many years have they been working there? What is their education level? Because those types of things affect your salary. So maybe if we add some variables, we could break the data down a little bit more to get a better understanding of it. All right, that is all that we have for measures of position and outliers.